Hello everyone, and welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Ruda Deeb. I'm a principal at Geosyntac Consultants in Oakland, California, and the organizer of the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's call. This webinar will consist of a brief overview of SERDP and ESTCP by Dr. Robin Nissan, followed by a listing of a few of the upcoming webinars in the series. Following Robin's opening remarks, we will transition to the technical portion of the webinar. Today's event features two speakers who will discuss blast noise measurements and community response at DoD installations. First, Jeffrey Alnack will discuss a network of remote sensors for military noise monitoring. He will be followed by a short Q&A session. Our second speaker will be Dr. Ed Naikaza, and Ed will speak about investigation of community attitude towards military blast noise. Following Ed's presentation, we will have a short Q&A session and then a longer Q&A session towards the end of the presentations before we wrap up. I would like to remind everyone that today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit your questions in advance of that session. With over 100 attendees on today's call, it is logistically challenging to open all the lines for oral questions. So we'll keep your lines on mute throughout the presentation. With that, I would like to introduce Dr. Robin Nissan, who is the SERDP ESTCP Program Manager for Weapons Systems and Platforms. Before joining SERDP and ESTCP, Robin was with Navarre's Weapons Division, China Lake in California, and he was there since 1984. Robin, please go ahead.
Thank you very much, Rula, and thank you everyone for calling in and signing into this webinar series. I'm going to give a brief overview of SERDP and ESTCP, and to start with, SERDP, Strategic Environmental Research and Development Program, was established in 1991. It is a collaboration between DoD, DOE, and EPA. We are a requirements-driven program, and we identify high-priority environmental science technology investment opportunities which address DoD requirements. We do fundamental research and advanced technology development to meet those goals. ESTCP, the Environmental Security Technology Certification Program, is a demonstration program, and we fund innovative, cost-effective environmental and energy technologies. We like to capitalize on our previous investments, sometimes made by SERDP, sometimes made by others, and we look to transition technology outside of the laboratory and into the field. And we also are very interested in implementation. We have 5 program areas, and they're listed here: energy and water, environmental restoration, munitions response, resource conservation and climate change, and weapon systems and platforms. Today's presentation is in the weapon systems and platforms arena. In weapon systems and platforms, 3 major areas: manufacturing and maintenance, and here we're looking at weapon systems and paints and coatings and repairs. And the second major area is green energetics, environmentally acceptable energetic materials. And finally, air and noise emissions is an area that we also invest in, and which we'll be discussing at today's webinar. So, in addition, what I wanted to say is that the webinar series has been quite successful, and based on feedback that we've had and attendance, we've decided that this will continue throughout the rest of this calendar year. So the listing on this view graph is what we think will be our calendar throughout the year, but I should mention that this could change, and you should check out our webinar series on our website to find out when topics of interest are available. As you can see, the topics that are listed right now cover the entire spectrum of our program. With that, I will pass it back to Rula, and we'll get on with the technical portion of this webinar series.
Thank you, Robin. And now it is my pleasure to introduce Mr. Jeffrey Alanak, who is a principal scientist at Applied Physical Sciences Corporation in Connecticut. Jeffrey's current area of research focuses on the development of acoustic tracking systems for unmanned underwater vehicles. He has been actively involved in the development of signal processing and systems designed for passive and active sonar systems for the past 10 years. Jeff has performed as a principal investigator and technical lead on a broad range of DoD-sponsored projects and has worked extensively in the fields of sonar systems design and modeling, detection, classification, as well as acoustic communications. With that, I'll turn it over to you, Jeff. Thank you so much for agreeing to be with us today.
Thanks, Rula. Good afternoon, everybody, and good morning to others on the West Coast. Today, I will discuss the development and demonstration of a network of remote sensors used for monitoring military noise at U.S. installations. Research, design, and subsequent demonstration of this system has been funded by both SERDP and ESTCC. In this webinar, I will discuss the purpose for monitoring military noise, the technical challenges, and our technology solutions. The overall goal for this project was to research and develop improved methods for measuring military blast noise at U.S. installations. Research into this area has led to the commercialization of a new noise monitoring technology we call BAMAS. This is an acronym for Blast Noise Bearing and Amplitude Measurement and Analysis System. We will discuss the design of the system, the results from a large-scale demonstration, and its benefits to our end users. The U.S. Armed Forces maintains a constant state of readiness by conducting testing and training activities at its military installations. This includes training with large weapons, heavy artillery, and explosives. Blast noise, which is the sound generated by these exercises, is an unintended byproduct which can negatively affect residential communities that surround the base. In the past decade, military installations have begun to use noise monitoring systems to measure and archive blast noise to better understand how it impacts surrounding communities. These systems are a critical tool not only for understanding how blast noise propagates into the communities, but also so that noise managers are aware of when noise begins to exceed acceptable levels. In this way, real-time feedback of noise levels from these systems is a vital component for all military test installations. So continuous and unintended monitoring for noise in remote areas presents a unique set of challenges that most commercial noise monitoring systems aren't adequately designed for. Typical outdoor noise monitors leverage conventional sound level meters, as you see in the picture in the bottom right there. They're not, and these aren't specifically designed for continuous outdoor use. They're mostly laboratory-grade systems. One of the major problems with these existing sensors is their susceptibility to falsely recording wind noise, which is commonly referred to as wind triggers. Wind triggers can overwhelm the user with thousands of false records, which renders meaningful assessment of noise levels challenging, if not impossible. Military testing is a 24/7 operation, thus the noise monitors must also function in all weather conditions. False recordings from other sources like cars, aircraft, thunder, animals is also a major problem. Given the importance of the data that's collected by noise monitoring systems, SERDP released a statement of need back in 2003 calling for the development of an improved noise monitoring system. So beginning in 2005, my company, APS, began researching new methods for measuring and archiving blast noise. The picture on your right here is an illustration of the result from that work. In order to mitigate the problem with wind triggers, the BAMAS noise monitors use a tetrahedral microphone array, which is that array at the top of the mast there. This is used to reject noise events that do not propagate at the speed of sound or those which have low spatial correlation. Since wind noise is spatially incoherent and travels orders of magnitude slower than the speed of sound, This array-based approach is an effective means to reject wind triggers. The noise monitor we developed also includes an onboard classification algorithm which can automatically recognize the type of sound. So for example, our system will label each sound recording as one of several different categories, including blast noise, small arms fire, cars, aircraft, wind, and thunder. This capability was developed at researchers at the University of Pittsburgh, and this is an extremely useful tool for noise managers whose job it is to monitor noise emissions. So that way they understand not only what the sound levels are, but what is the sound that's being created that could be propagating into the residential community nearby. One of the major features of the system is its ability to measure the bearing of a blast noise event. With multiple noise monitors, the system is able to triangulate the location of the event. This is immensely helpful in understanding where on base the blast originated from. So land use near military installations is a growing issue. As new residential and commercial development moves closer to the base, the impact of blast noise will become greater, albeit the base may have been conducting the same testing for many years prior. The map shown here is a hypothetical scenario to demonstrate this issue. Residential communities surround the base in blue, as these locations here. The red areas are impact zones, and these orange dots are individual firing points. So it's important to note that military bases can have hundreds of different firing points, and they're all shooting into the impact zone. So the objective here is to surround the base with noise monitors, which are these red dots here. Military bases generally have a few hundred different firing points, all of which may or may not have an impact on adjacent communities. Noise monitors must be installed around the perimeter of the base in order to provide a complete coverage. The locations of these monitoring stations are very remote and sometimes very difficult to access by car. They are generally left unattended for months at a time, if not years. So the BAMAS system, which is what we developed for SERDP and continue the research for ESTCP, is a network of noise monitors intended specifically for remote and unattended operations. Each noise monitoring station includes a solar panel, shown here, and power, and a cellular modem, which is a little antenna here, for data transfer. Special signal processing algorithms were developed to properly detect blast events and reject other foreign sources of sound. The noise monitors are capable of recording and classifying sounds from aircraft overflights and small arms fires. So data that's collected by the BAMAS noise monitors is sent to a base station computer where it is stored in a database. The base station also hosts a website that end users may access, which is shown here on the right. The website displays detected blast events in real time or historical data for a previous day, week, month, or year. In this example, we're showing 6 BAMAS noise monitors on your left here, which are represented on the GIS map by green waypoints. The red lines emanating from each of the green waypoints indicates the bearing to the origin of a blast event. So where red lines overlap each other, for example in this case here, indicates the estimated position of a blast event. So this tells the noise manager where on base that event was created. So that way they can better plan their exercises accordingly. So noise metrics for each of the sound recordings are displayed in the table below. So this is a function of time, indicates the name of the noise monitor, the sound level here, the type of sound that was recorded, blast noise, aircraft, thunder, etc., the bearing of the event, and the elevation angle. As I mentioned earlier, SERDP initiated the research and development of the system back in 2003. After we developed the underlying technology solution with SERDP, ESTCP funded us to demonstrate that it can work in a real operational environment. The objectives of our research with ESTCP was to demonstrate the system is reliable, that it can run continuously over long periods, validate the detection and classification algorithms work, and to develop a user interface. Another big goal was to get this technology in the hands of the users through commercialization and outreach. While technology research and development is our main objective, transferring the technology into a product to deliver to our end users was our guiding principle. demonstrate the BAMAS system is a viable technology, we built 9 monitors and installed them around the perimeter of a large U.S. military installation. The monitors were left unattended for 12 months to collect noise data, and we conducted post-analysis to verify system performance. Over the course of 12 months, the system analyzed over 33 million sound events exceeding 95 decibels. Of those 33 million events, over 450,000 were recognized by the system as either blast noise, aircraft, or small arms fire. The blast noise was by far the majority of those recordings. As part of our initiative to get the end users involved, we provided them with a link to the website during the 12-month exercise. They used the website periodically to investigate large events and in some cases to determine which firing points were actively shooting. This is a picture of one of our BAMAS noise monitors installed in a remote area at our demonstration site. The tetrahedron microphone array is located at the top of the mast, is used to measure the sound direction and to mitigate wind triggers. The small electronics enclosure at the base of the mast is comprised of a low-power computer, cellular modem, deep cycle battery, high-accuracy reference microphone, and a wind speed sensor that you can see right here. The signal processing algorithms were developed for detection and classification are hosted in a low-power computer on a fixed-point processor. So rejection of wind triggers is one of our key performance metrics. Over the course of a 12-month experiment, we demonstrated that BAMAS noise monitors reject over 99% of wind events. The data shown on this slide best illustrates that capability. Here I'm showing 3 plots of wind speed, sound pressure level, and bearing over a 10-hour interval. In the morning between 9 a.m. and noon, the wind was relatively calm, and the noise monitors were detecting artillery shots and explosions on multiple bearings. So for example, if you look at the bottom plot where the bearing is, we were detecting artillery shots roughly at 0 degrees true north and about north-northwest, so 0 and 300 degrees. And the corresponding sound pressure level for those events varied. During the morning, it was very calm. The winds were between 0 and 5 miles per hour, but at noon, a large weather front came in, and the wind picked up from up to 15 miles per hour. So all the red dots you see on this plot after noon indicate an event, a recording on our system that was rejected because it was considered to be a wind event. There's a couple things to notice here. There are thousands of wind triggers that are being rejected. And although we were rejecting a lot of wind events, we continued to detect the artillery shots that continued from the morning into the afternoon. So you can see the black dots here that from true north we continued to detect those events into the afternoon correctly. So another key feature of the system is its ability to triangulate the location of blast events. Since each noise monitor provides a measure of bearing, 2 or more noise monitors that detect the same noise events may be used to triangulate its location. The satellite image here is actual data reported by our system. Noise monitor number 1, which is located in the southwest, has detected several blast events from about due east. And noise monitor number 2 in the northwest has detected a number of blast events from the southwest. The overlap of these red bearing lines indicates the precise location of the shot. The bearing accuracy of the system is generally very good, say within a few degrees. However, wind and refraction of sound in the atmosphere can strongly influence this measurement. Given military bases can have hundreds of different firing points, this is a very useful feature for our end users in order to indicate which firing point on base is active and which one could be causing higher noise levels at the perimeter. So, for example, we found that our users use our system to determine which firing point is active on base. So end users of the BAMAS system can get access to an archive of noise data through this website. Blast noise recordings are displayed visually on a GIS map shown here, and as a function of time in the table below. If the user clicks on an event within the table, for example, this red bar the user clicked here, it actually renders an illustration of the waveform in this box here. This also allows them to replay the data so they can listen to what the sound recording was. So although our software already classifies each sound recording, the user may replay it in order to verify what it was. So all data may be exported from the website as an Excel spreadsheet or in a KML file, which can be imported into Google Earth. In addition to analyzing noise data online, our end users can also check the health status of their noise monitors through this website. So this page right here indicates a health monitor. There were 9 noise monitors installed for our demonstration site, and this health monitoring page tells you the result of several different self-tests that the system runs, battery voltage, and relevant system level voltages, and tells you when the last time is heard. Because the noise monitors are installed in very remote areas, our end users oftentimes can't get access to them easily, so this offers them an easy way to verify that the system is healthy. So noise monitors are a vital tool for real-time feedback and assessment of sound levels created by blast noise. The BAMAS noise monitoring system presented during this webinar is the result of several years of research followed by a large-scale demonstration. The technology developed is now a commercial product and is being used at several installations across the country. So I'd like to thank SERDP and ESTCV sponsors for the opportunity to speak today. For those of you who would like to learn more about this project, there's a web link here to the ESTCP site, or you can visit www.afisci.com/BAMAS, which is our company website. So with that, I'll pass it back to Rula.
Yes, thank you, Jeff, for a very informative presentation. We've received a number of questions, and I'll start off by reading the first one. Can you please tell us how much effort is involved in designing an array for a large military installation?
Much effort. So the design of the array was based upon empirical data that was recorded with a much larger array based on experiments from several years ago with SERDP. The aperture of the array was chosen to provide us good bearing accuracy measurements.
Great, thank you. Can you tell us whether federal real estate licenses were procured for the off-site location in your slide 22?
You're back to slide 22. Can you repeat it? Were federal
real estate licenses procured for off-site locations? Are you aware of?
We don't have any. There were no real estate licenses that were required.
Great.
We worked with the military installation in coordination with them and received.
All right. How does this system compare to other commercial noise monitors?
So, as I mentioned a little bit earlier, the BAMAS noise monitoring system is specifically designed for military installations. So, in addition to the tetrahedral microphone array, that's probably the thing that probably stands out the most, being that it's a multi-channel noise recorder. A lot of the commercial noise monitoring systems are just a single channel, so they can suffer from recording false wind triggers. That was probably the largest thing that stands out. On top of that, the website we've designed is really tailored for U.S. military installations, so that they can be apprised of the sound levels at the perimeter and where the sound's being created from.
Thank you. Can you tell us what the peak sound level that can be measured is?
This system is capable of measuring up to 145 decibels.
Excellent. Have you considered using oversized windscreens to protect the Type 1 microphone from wind-induced noise?
Yes, that has been an area of research that we've looked into. We find that the windscreens just sort of, from a practical standpoint, they get damaged from being out in the weather for a long time. The BAMAS system is, installed and maintained maybe a few times a year. So we found that a lot of times the birds and things would get on the windscreens and kind of be digging at those. So the using an array is a simple approach, but it also offers the added benefit of measuring the bearing of the event as well. So we get two benefits. We get the benefit of measuring the bearing, on top of wind trigger rejection.
Thank you. And can you tell us whether you have to do NEPA to install these monitors?
Do we need to do what?
NEPA?
I'm sorry, I'm not sure what that is.
All right, let's skip over to the second
I'm going to
question.
bust in and say that's an environmental assessment to see if there's any impact of that technology.
This is a noise recording system, so this might be used in addition, in coordination of performing a NEPA, perhaps, to measure what the sound levels are.
But you didn't have to do one for this technology to be installed. Okay, thank you.
Thank you both. From slide number 12, it appears that the SPLs of blast events during high wind were higher than SPLs of blast events during low wind. Can you tell us whether those levels are influenced by wind noise or if the blast recordings are actually louder?
That's a very good question. So, for example, the measurements I was actually showing you peak sound pressure level as opposed to an RMS sound pressure level. In which case, it is that measurement of peak is most definitely influenced by just wind. Other measures of noise metrics are less susceptible to that. And Ed Nikeza, who will be talking next, has several metrics which he has been working on, which coincide with how communities respond to noise. Thank
you. And can you tell us whether your system records octave band data?
Yes, it does record octave bands.
All right, and one last question for you, Jeff, before we transition on to Ed's presentation. Can you tell us how many of these systems are currently being used on ranges and what the expected cost of each of these monitoring systems is?
Sure. So we have, there are 3 military bases that use BAMAS noise monitoring systems. One of the bases has 5 noise monitors, another has 9, and another has 3. This technology was just launched, maybe a year and a half ago, so we just sort of began working with our end customers. What was the last part of that question?
The expected cost of each monitoring system.
For that, I would like to, you can actually look our system up on the GSA Advantage website. So federal customers are able to purchase it from there. So I would like to reference that.
Wonderful. Thank you, Jeff. You did an awesome job with the questions. We thank you for this, and we'll be asking you additional questions during the final Q&A session. But right now, we're going to go to the second speaker in this webinar series, who is Dr. Edward Nikeza. Ed is an acoustical engineer with the Engineer Research and Development Center. He is also an adjunct professor of acoustics at Columbia College Chicago. At ERDC, Ed leads multidisciplinary teams and also manages a diverse research portfolio ranging from basic to applied research. Some of his contributions to the military community include algorithms to rapidly estimate noise levels over a large region with technology, with a small number of noise monitors, leading the demonstration of new military noise monitor technology and research findings that support the community tolerance hypotheses. While working full-time at ERDC, Ed recently finished his PhD in acoustics through Penn State with support of the ERDC Long-Term Training Award in 2011. He is also the recipient of the L.R. Schaefer Research and Development Achievement Award for advances in sleep disturbance from blast noise research. With that, I'll turn it over to you, Ed. Please proceed.
Thank you, Rula, and thank you for the nice introduction. So good afternoon, everyone. Today I'm going to tell you about a 5-year SERDP-funded study that we recently completed, which investigated community response to military blast noise. When I say we, I'm specifically referring to my colleagues at the Engineer Research and Development Center, the Penn State Applied Research Laboratory, and Tetra Tech. Okay, my agenda is as follows. I'll start by giving you some general background material that will explain why and how we conducted this research. I'll then discuss the results of our study. I'll go over the recommendations we made, and then I'll end my talk with some ideas on how we can implement the results from this study using the noise monitor technology that Jeff just told us about. For over 40 years, the United States military has had an abiding interest in understanding how humans and communities respond to blast noise. There is both an obligation to inform the public about the environmental consequences of noise and blast noise, and a concern about the loss of training lands and capabilities caused by the implementation of curfews and restrictions due to the negative community reaction to blast noise. The bottom line is that blast noise costs the military time and money. For example, it is a matter of record that blast noise has resulted in the closure of ranges and the delay, cancellation, and rescheduling of testing and training activities. Noise is often cited as a reason for purchasing land through the Army Compatible Use Buffer Zone program, also known as ACUB, and there is a cost associated with the handling of complaints and damage claims. But the biggest cost is the cost of military readiness due to the loss of testing and training lands and the implementation of curfews and restrictions. Now, when I refer to blast noise, I'm specifically referring to high intensity impulsive noise emitted by large weapons, heavy artillery, and explosions. Unlike transportation noise levels, which occur in regular patterns throughout the year and have small day-to-day variation, blast noise events occur intermittently, and the noise levels vary drastically from day to day. It is not uncommon to have several consecutive days of intense, often loud training exercises interwoven with periods of relative quiet. Blast noise contains a lot of low-frequency acoustical energy, which essentially means it can travel rather efficiently through the air. And as a result, blast noise can be heard at distances of up to 20 kilometers from the source. This means that the blast noise footprints can encompass many communities living both on and near our military installations. To make matters worse, received blast noise levels can vary by as much as 50 decibels, 50 dB, due to the variability of the weather. And just to be clear about the significance of 50 dB, that spans the range of a sound being barely audible or noticeable to being so loud that you are likely to jump out of your seat. Predicting how individuals and communities will respond to blast noise is a notoriously difficult problem, and perhaps even more difficult challenge than estimating noise environments. Annoyance to noise is a subjective psychological phenomenon, and the circumstances that drive someone to complain are often numerous and complex. The fact of the matter is that humans are complex and the responses are subjective. In fact, we often find that the factors that have the highest correlation with human and community response are non-acoustical factors. In a related manner, there is a growing body of literature which suggests that each community has a unique tolerance to noise. Recent studies have shown that they can better predict how communities will respond to noise if they analyze each community independently rather than combining data across study sets. While I think there's some truth to these results, it still remains to be seen whether the superior dose-response curve fits obtained by analyzing each community individually are due to the actual differences in community tolerance, or if these superior fits are merely an artifact of the errors and uncertainties implicit in the differing noise measurement and community response procedures used between study sites. Now, going back to the focus of this talk, which is predicting community response to blast noise, there's a concern about the methods that are currently used to predict that community response to blast noise. As a result, SERDP put together a statement of need in 2006 in an effort to enhance our understanding of how individuals and communities respond to military blast noise. The objectives, as written in the statement of need, are as follows. We were instructed to, 1, investigate the metrics currently used by the U.S. military to assess blast noise and to assess whether these metrics adequately account for the intermittent and impulsive nature of blast noise events. I will talk a little bit more about the metrics during this talk, but we'll mostly focus on the methods used to assess community response. We did, however, take a comprehensive look at the metrics that have been used to assess military blast noise over time, and I will simply refer you to a 2013 Military Operations Research Journal article where we take a look at the evolution of metrics used to assess community response to blast noise. There are, in fact, 2 methods that are currently used to assess community response to military blast noise. These are given in Army Regulation 200-1 and include annoyance predicted by a long-term or yearly average noise level, namely the C-weighted day-night level. This method is used for long-term planning purposes. For example, where to site a new range, or when an environmental impact statement or NEPA assessment is warranted. In terms of managing blast noise in the near or short term, a complaint risk criteria is recommended. That is, the risk of receiving blast noise complaints is predicted by the maximum unweighted peak level. Here is a figure that shows the raw data and the resulting dose response curve that underlies the current blast noise assessment method. In particular, this figure shows the proportion of respondents that are highly annoyed, also known as the percent highly annoyed, as a function of the C-weighted day-night level, or CDNL. The data shown in this figure comes from 5 studies that took place between 1965 and 1995. There are 2 community response to sonic boom noise studies and 3 community response to military noise studies, which include Fort Bragg, Fort Lewis, and the Swedish study. Now, obviously, there's a good scattering of data here, but I think that the bigger thing I want you to take away from these studies was the fact that during the time when these studies occurred, we did not have reliable noise monitoring equipment. As a result, the dose or noise component of the study was estimated with a prediction model rather than measured. And it's really hard to know whether these models adequately captured the intermittent and impulsive nature of blast noise environments over the entire study time periods, which are reflected through the data here. The other way that noise is managed and assessed is through a complaint risk criteria. Here is a table that shows the risk of receiving a blast noise complaint as a function of the single event unweighted peak level. The data that underlie this criteria also come from a study in the 70s. And unlike the community annoyance model shown on the previous slide, this criteria is only recommended in Army Regulation 200-1. That is, it's given as a supplemental method that installations can use to manage complaints. What I'd like you to keep in mind as we move forward with this presentation is the fact that this criteria is based upon the data from one installation that was captured in the 70s. The two other objectives in the SERDP Statement of Need were to examine the relationship between individuals that complain and community annoyance. The underlying research question here is, to what extent do individual complaints give an indication of the general community annoyance? And the basic idea is that if those who complain about the installation represent the general community, then complaint information could be used as an indicator or surrogate measure of community annoyance. I'll discuss this objective in the research we did in more detail in the upcoming slides, but in case I fail to mention it later, you can refer to a 2013 Journal of the Acoustical Society of America paper where we specifically examined this exact research question. The last objective in the Statement of Need was to recommend criteria that can be used to actively manage noise at installations so that the sustainability of testing and training is ensured. I'll spend the last part of the talk discussing our recommendations from the studies that we did as part of this project. And for those of you who are interested in the finer details, I will refer you to our final report. The report is available on the SERDP website, or feel free to contact me directly. So what did we do? Well, the first thing to note is that we decided to take a measurement-based approach to our research. Recall that previous studies used prediction models to estimate the noise environment rather than measuring the blast noise environment. This was a rather ambitious undertaking, and we essentially tried to measure each and every blast noise event that occurred at each of the 3 study sites over a roughly 1-year time period. Our studies were conducted at 3 military testing and training facilities spread across the continental U.S., which varied in terms of geography, local meteorology, and community demographics. At installation or study site A, we conducted complaint research in a general community survey, abbreviated GCS, in the table. The asterisk in the table represents the fact that we did not use the general community survey data from study site A in our final analysis, but rather there were some key lessons learned during the blast noise measurements at this site that we used to refine and improve our noise data collections at study sites B and C. In the end, there were 4 main studies that comprised our SERDP research: 2 complaint studies, an in situ survey, and a general community survey. The complaint survey looked at the relationship between those who complain and the annoyance of their non-complaining neighbors. Recall this specifically addressed research objective 2, examine the extent to which individual complaints are indicative of general community annoyance. The complaint study looked at the probability of receiving blast noise complaints, which specifically addressed research objective 1, and examined the utility of the current complaint risk assessment method that is in Army Regulation 200-1. The other 2 studies were an in situ and general community survey study, which were more labor-intensive measurement-based studies that also addressed research objective 1, but more so in terms of annoyance than complaints. The in situ study was designed to enhance the understanding of how individuals respond to blast noise events over a short time period. We set up equipment at residents' locations and measured both the noise environment and their responses. And then the general community survey was designed to enhance the understanding of how communities respond to blast noise over a longer time period, for example, on the order of weeks, months, or years. Collectively, these studies in our measurement-based approach were instrumental into achieving Objective 3, which, as you may recall, was to recommend improved blast noise assessment criteria and management procedures. So, across all the study sites, blast noise was clearly the most annoying noise source among the 8 sources which we asked on our general community survey. Here, the vertical axis is showing the percent highly annoyed. Percent highly annoyed is calculated using a 5-point Likert scale ranging from 1, not at all annoyed, to 5, extremely annoyed. To be more specific, this calculation is made by tabulating the number of respondents that give an annoyance rating of 4 or 5 and dividing it by the total number of respondents. This method, that is the percent highly annoyed, is the standard method that is used in virtually all community response to noise studies. There are pros and cons to this approach, that is taking the 5-point response data and collapsing it into binary data set, but I'll leave that discussion for another time or as a question to follow up afterwards. During our complaint research at Study Site A, we found that those who complain about blast noise report much higher annoyance than their non-complaining neighbors. This time on the vertical axis, I'm showing the mean annoyance across that 5-point scale to the complaint reference blast event, or abbreviated CRBE. For this study, each time a blast noise complaint was made to the installation, we followed up with the complainant and then surveyed at least 9 of the complainant's non-complaining neighbors to get a sense of their annoyance to the complaint reference blast event. There are a few things to note about this finding. First of all, we found that not all of the complainants reported having extreme annoyance, which you can see by looking at the bar to the right. Actually, 2 of the complainants responded that they had no annoyance at all, and were actually not complaining, but were inquiring about whether the loud noise that they heard came from the installation. In fact, they were relieved when the installation confirmed that the noise had actually come from the installation and not from somewhere else. I mention this because it brings up 2 points. One is that installations should be careful to note the difference between somebody who is complaining and someone is inquiring, as they might deal with those situations differently. And 2, it provides some feedback from the community that they would like more transparency in knowing who the noise has come from, which is something that we could achieve with the noise monitoring systems that Jeff has just talked to us about. But I think the main thing to take away from this figure is simply that the non-complaining neighbors, referred to as matched sample given on the left, have much lower annoyance than the complainers. This really calls into question on how installations should deal with complaints, and at the very least gives some evidence that testing and training curfews and restrictions should not be implemented to appease a few individuals when they do not represent the community at large. Now, I am not suggesting that complaints should be ignored completely. As we know, unacknowledged complaints are often the ones that escalate into congressional inquiries and lawsuits. During our complaint research, we also looked at annoyance to general military noise and found that annoyance increases as the complaint status increases. We found that several of the complaints that we received were from folks that had previously complained to the installation. As one might predict, those repeat complainants or complainers had more general annoyance to military noise in general than those who were complaining for the first time, and significantly more annoyance than those who had never complained to the installation before. This also gives us additional support for the idea that complaints should be dealt with in a timely manner so as to keep complaints from escalating into a bigger problem. In addition to looking at the relationship between individual complaints and annoyance, community annoyance, we also looked at the probability of receiving a blast noise complaint as a function of the blast noise level. This work was also done at Study Site A, although at a different time period than the 2 previous studies. When we analyzed all of the noise monitor data and complaint data together, we found that the probability of receiving a blast noise complaint was actually rather low, and that high levels, for example, unweighted peak levels greater than 120 dB, occur often and without complaints. We also found, however, that the probability of receiving a complaint was high in a few communities. This supports the idea that some communities may be more or less tolerant to noise, which is commonly referred to as the community tolerance hypothesis. As you can see, the red line in this figure shows the probability of receiving a blast noise complaint from community members living near noise monitor 7, that probability increases as the blast noise level captured on monitor 7 increases. One thing you might be thinking to yourself is, why aren't the results shown in terms of the unweighted peak level given that the current complaint list criteria is given in terms of unweighted peak levels. In our analysis, we found that it was actually the C-weighted day-night level, calculated over a 24-hour time period, better predicted the probability of receiving a complaint than the current standard metric, the maximum unweighted peak level. Okay, there's a lot going on here on the slide. So before I go over the details, let's very quickly remind ourselves of the first objective of the research, which was to assess whether the current metrics adequately account for the intermittent and impulsive nature of blast noise events. If we start by looking at the bottom half of this figure, we can see the daily or 24-hour C-weighted day-night level captured in community B3 over the entire one-year study. Each individual day that at least one blast noise event occurred in this community is notated with a black dot. When there are days in which consecutive blast noise events are heard, a solid black line is drawn, and a dashed line in the light gray is used to show the general smooth or average trends over the study time period. The first takeaway from this figure is that blast noise environment is highly variable and dynamic. Blast noise events occur intermittently throughout the year. There are periods of noise activity followed by periods of relative quiet. And it really begs the question of whether blast noise should be assessed using a yearly average noise metric that essentially takes all the data shown in this figure and distills it down to one single number. If we now focus on the top half of this figure, we see that the annoyance response to blast noise is also variable and dynamic. It is also interesting to see that those who were surveyed report a very similar amount of annoyance when asked to rate their annoyance to the blast noise environment over the past 4 weeks and over the past 12 months. The exception, of course, being the survey data gathered in May, where there's much lower annoyance to the 12-month blast noise event than the 4-week blast noise environment. I do not, unfortunately, have a good explanation for why we see this outlier, but beyond the fact that asking someone to remember the noise environment over a long time period is a difficult task. I know that if somebody asked me to rate my annoyance to a particular noise source over the past year, I would be more likely to give a general feeling for kind of my historical noise environment rather than being able to remember a specific time period. Now that point, the point being, of course, is that we are dealing with a very subjective response. Okay. This figure shows the results of a more traditional dose-response analysis in comparison to the previous slide. Here we can see the percent highly annoyed as a function of the C-weighted day-night level for 5 communities that were located at study site B and C. The numbers associated with the communities have significance as both B1 and C1 represent a community living on the installation, whereas communities B2, B3, and C2 were located adjacent to the installation. The dots on this figure are showing the percentage of the community that were highly annoyed to the blast noise environment captured over the past 4 weeks. The size of the dots is weighted to give us a sense of the number of data points that make up each dot. For example, the large dots represent a large number of surveys on the order of tens or hundreds of responses, whereas the smallest dots may include less than 5 respondents. Lastly, a solid weighted regression line is drawn through each community's data points so that we can visualize the general trend of the data and the range of the blast noise environment in each community. The general takeaway is that each community has a unique tolerance to blast noise. It is also perhaps not surprising that communities B2 and B3 have the most annoyance, given that they are most consistently exposed to high noise levels with CDNL levels in the range of 45 to 65 dB. This is, of course, consistent with what we saw in one of our first slides, where study site B had the most annoyance to blast noise in comparison to the other study sites. It is also interesting to note that the communities living on the installation report the lowest annoyance, as we might expect given that all of the study participants were either active military or spouses of active military members. However, we do see that community B1 was exposed to much lower noise levels than the off-post communities of B2 and B3. In contrast, we actually do find, though, in community C1 that there is as many as 15 to 20% of that on-post community that were highly annoyed, which is not an insignificant amount. I know that one of Public Health Command's mission deals with the quality of life on installation, so I think this is a significant piece of data. But the last thing I want to leave you with is that there are a few caveats to this data. The first caveat is that we are less certain about the noise gathered from study site C in comparison to study site B. In short, we used a blast noise classifier that was trained at study site B to classify the noise events at study site C. I will spare you from the details at this time and will refer you to our final report where the issue is discussed in detail. The other caveat is that this dose-response model ignores the responses to the other 50 or so questions that were asked as part of the general community survey. In that sense, there are no covariates included or no non-acoustical factors accounted for in this model. In fact, when we did a more elaborate analysis of the data, which included non-acoustical factors, we did not find such a strong difference between each community's tolerance to noise. All right. So in our more elaborate analysis of the general community survey data, we found the following non-acoustical factors contributed to community annoyance. For the following 6 non-acoustical factors, we found there was an increase in annoyance if the respondent indicated that there was a time of day in which blast noise was most disturbing, if they spent more time at home between the hours of 6 and 10 p.m., on average in comparison to the other surveyed. So again, telling us that the time of day that blast noise events happen is important and affect the response. If there was an indication that noise had disturbed them, that is irritated, startled, or frightened them in the past 12 months, there was more annoyance. If they reported hearing blast noise very frequently, on average, then there was more annoyance. If they thought their neighborhood was an excellent place to live, there was more annoyance. And if the respondents ever experienced more than one object rattling in response to blast noise, there was also more annoyance. Now, these findings are congruent with the literature which has pointed out the importance of these non-acoustical factors. There are additional non-acoustical factors. However, when we look at these, we also found that there was a decrease in annoyance if more than an average number of adults lived in the household, which may be an indication of the socioeconomic status of that respondent. There was also a decrease in annoyance if the importance of the installation was larger than average, if the respondent lived in a single-family attached home, and if the respondent self-reported that they could habituate to noise, that is, get used to noise over time. This project was successful in the fact that we achieved all 3 of the SERDP Statement of Need objectives. When we account for the findings across all of our study sites and experiments, we find that the current methods used for predicting community response to blast noise have low predictive validity and do not account for the intermittent and dynamic nature of blast noise environments that occur on and around our military installations. But we also found that there was no conclusive evidence to suggest moving away from using the C-weighted day-night level to predict community annoyance. This statement, however, has a caveat in that we found a higher correlation between community annoyance and the C-weighted day-night level if we looked at data gathered over a short time period, for example, 4 weeks, in comparison to data gathered over what the current standard recommends, which is 9 to 12 months. We did, however, find sufficient evidence to discontinue the use of the unweighted peak level for managing complaints. Rather, we found that, again, the C-weighted day-night level, calculated over a 24-hour time period, had a better correlation with complaints. In regards to Objective 2, we found that the opinions of individual complainants do not represent the general community opinion of blast noise. However, blast noise complaints should be dealt with in a timely manner in order to diffuse the situation before it escalates into a bigger problem, as we talked about before. And in regards to the last objective, we recommend the following to actively manage noise at installations so that the sustainability of the testing and training mission is ensured. I should point out that the key element to this statement are the words actively manage. We are thus making recommendations to help with the day-to-day management and short or near-term assessments and predictions. With that in mind, we recommend that installations manage noise on a community-by-community basis, that they use the C-weighted day-night level, calculated over a 24-hour time period to manage complaints, and that the C-weighted sound exposure level be used to quantify and assess individual blast noise events. The beauty of these recommendations is that if we are able to measure the C-weighted sound exposure levels of single events, those same measures, the single event sound exposure levels, can then be used to calculate both the day-night level over a 24-hour and 4-week time period. I will expound on these recommendations on the next 3 slides. The assessment and management of blast noise on a community-by-community basis can be accomplished by using noise monitor technology, such as the technology Jeff recently told us about. With this technology, we will be able to measure single event sound exposure levels and thus be able to calculate both the 24-hour and 4-week C-weighted day-night levels. In terms of managing and assessing complaints, we recommend using the C-weighted day-night level calculated on an hourly and or daily basis. In addition, we recommend that the complaint risk should be managed on a community-by-community basis. Further, we find some evidence that there is an increase in the percentage of the community that will be highly annoyed when the C-weighted day-night level exceeds 60 dB, and an increase in the percent of the community that will not be annoyed if the levels are below 45 dB. These thresholds can and should be used as starting points when building those community-specific response models. Lastly, in order to be able to build community-specific complaint criteria and response models, a centralized noise and complaint database will be needed. Our last recommendation is that the C-weighted sound exposure level be used in place of the unweighted peak level to quantify single blast events. If this is adopted, then a single event not to exceed threshold of 118 dB should be used, as it is approximately equivalent to an unweighted peak level of 140 dB, which is the threshold of where human hearing damage can start to occur. Along those same lines, caution should be exercised if those single event levels start to approach the hearing damage threshold, and as such, we recommend that installations exercise caution if they receive single event levels that approach or exceed a level of 112 dB. I'd like to conclude this talk by leaving you with some ideas for how the findings and recommendations of the SERDP project can be implemented to provide real-time feedback and forecasting tools for the purpose of actively managing noise and sustaining the testing and training mission. I will start at the left, and I'll talk about this going in a clockwise manner. A key component to being able to actively manage and assess the noise produced by testing and training installations is the ability to measure each and every military noise event. As Jeff told us, until recently, this has not been possible or feasible. Having reliable noise monitoring equipment, however, is only half the battle. Picture having a few monitors spread across a large community or some large region of interest. More times than not, we will be interested in knowing the noise level between or beyond the locations of the noise monitors. Or better yet, we would like to see a noise map based upon the noise monitor data. Research is currently underway to further develop geostatistical models to provide probabilistic noise maps. That is, a noise map that provides both an estimate of the noise level and the uncertainty associated with that estimate. Now, with this information and the new community response findings that I talked about today, we can then translate the noise maps into noise impact maps. An example of such a noise impact map is given in the lower left-hand corner of the slide. With this type of infrastructure, it should not only be possible to provide real-time feedback of the current noise environment, but we should also be able to use the data to learn more about the local propagation environment, which in turn can be used to improve our existing propagation and forecasting models. The end result is a system that can automatically measure military noise events, that can predict and forecast the noise environment in areas where we do not have sensors, a system that can assess the environment in near real time to provide direct feedback and warnings to the installation about favorable times to make noise, or if the current noise levels are unusually loud, which ultimately will allow the installations to adaptively manage their noise and avoid unnecessary testing and training restrictions. I'd like to thank you for your time and attention. I would also like to thank SERDP and ESTCP for their support and a chance to talk with you today. For more details about our SERDP community response to noise work, please see the attached web link, and also please feel free to contact me directly if you have any additional questions. Thank you again.
Thank you so much, Ed, for a very fascinating presentation. We have a number of questions for you, starting with what are some of the non-acoustic factors that are good predictors of annoyance? For example, gender, age, support for the military, etc.
Okay, good question. Let me move back here to our slides. I'll just pull these up quick. Okay, so definitely the timing of events, I think, is a practical non-acoustical factor that could be incorporated in a model. I think that hidden behind some of these other types of non-acoustical factors, such as the neighborhood's an excellent place to live, and if I go to the next slide, the number of adults per household or the housing type, these might be getting at some of the demographic type of information that could be teased out from publicly available information. I know that there has been some research that has started looking into using demographic data such as age and gender and whatnot. To date, I don't think there hasn't been any conclusive evidence. However, this is still an open area of research. Lastly, I just wanted to say, yes, of course, the installation importance, right? Those who may have some economic ties to the installation or just really feel that these noises are the sound of freedom, which is something that we often get feedback about. Another interesting thing is this habituation to noise. So there is a certain type of personality that is able to better tolerate and get used to noise over time. And it's quite possible that through looking at some of the public
Did we lose Ed?
Oh, I'm sorry. Looks like my phone went on mute. I wonder where I got cut off.
We just lost you a few seconds ago, so if you just want to restart at the habituation to noise adjustments by certain groups.
Okay, thank you. Yes, so then also the habituation to noise, we find that a small percentage of the population is not able to habituate to noise, and also a percentage of that population is able to habituate to noise. It is possible that we could look at publicly available demographic information and try to come up with surrogate measures that actually capture some of these non-acoustical factors.
Great, thank you so much. Another question for you has to do with the with you mentioning that you are skeptical about the community tolerance hypothesis. Can you elaborate on that?
Sure. Yeah, that's a great point. I want to thank whoever brought that up. When we do these communities' response to noise studies, and let me just show you a good slide here. So, you know, if we look here at slide 47, the bottom half of this graph really starts to get at kind of the noise environment. And what we essentially do is we take that noise environment and we distill it down to kind of more condensed metrics to try and quantify. You know, for example, here I'm showing the noise level over a 4-week time period. Now, let's say, Rula, that you and I go out and do the same study, okay? Same location, same survey, but we don't coordinate on how the noise data is gathered. So you go out with your noise equipment, which may have some different parameters and thresholds that are used. You may record over a slightly different time period than what I did. You might have a different way of processing the data. And in the end, even though we've captured the same community response from that community, we may have captured different noise environments. So I just mentioned that, yes, it is quite possible that different communities may have different tolerances to noise, but we should also really question the way that the noise and the response is gathered. And it is possible that instead of actually being this major divide between communities, that it's really, we're just seeing the division between the different methods that were used to capture the data. Good question.
Yeah, this is completely fascinating. All right. Does the model that you use take into account community members that just want to complain about anything that the military does?
Let's see. So I'm not exactly sure which model, but I'll assume we're talking about a you know, some kind of complaint response model. So, you know, I think one of the big takeaways, right, with the complaint work, and actually this is probably the better example, was when somebody complains, the installation has an opportunity to get some feedback from that individual. And I know the operational noise group through Public Health Command has some information out there, has made some recommendations on a standardized way to capture complaint data. But I think in practice, we see lots of different methods, kind of local methods that are used to capture the complaints. So specifically to answer the question, the answer is no, that is not currently accounted for in the models, but it most certainly should be, because that adds another layer of detail to the model, which, you know, as I showed in this slide 44, we actually had 2 people complaining that simply were inquiring about the noise. And you could say the same thing along the lines of, you may have some people that are complaining actually not because of the noise was just an opportunity for them to really voice what they were really upset about, which was, you know, something else kind of related to the installation. So that happens, and yes, in moving forward, that does need to be accounted for.
Thank you, Ed. And can you tell us if the model takes into account weather, for example, the presence of clouds or cloud cover?
Okay. So was there more details in terms of, which model? Because, well, let's see. So let's just pull up this fit of the data. So this would be predicting the percentage of the population highly annoyed, right? You could consider this a model. The beauty of our measurement-based approach is that we do not have to rely on a prediction model to estimate what the noise environment is. And in that prediction model, you would have to input, what were the meteorological conditions at the times of the event. So in the way that we did our research, it didn't necessarily make a difference what the weather conditions were, because we simply captured what that noise environment was over the study period. Now, in the case that the question is asking, okay, so now we want to put together a criteria for a model of the probability of receiving a complaint, the answer again is yes. The model should take into account metadata, such as meta weather data, such as the amount of cloud cover, was there a temperature inversion. In our current versions of the models, they are not currently in there because, again, we used actual measurements. But in moving forward, where we do start to integrate the measurements with prediction models and then using that information to predict community response, both annoyance and complaints, then yes, we do need to account for that information. Good question.
Thank you. Thank you, Ed. How would you use your data to predict the long-term noise environment from a stationing action?
Okay, so see if we can follow this train of thought. Okay, so let me go just kind of a visual to think about kind of some of these big picture ideas. All right. So the question was specifically brought up about how can we use noise measurements to improve our long-term assessments. I assume by long-term meaning, on the order of like 9 months to a year, and probably related to environmental impact statements in NEPA. Okay. The current models which are used for those assessments are not site-specific in terms of accounting for the local propagation conditions. Okay? It does take into account kind of gross, large-scale meteorological conditions, but it doesn't go down to the fine resolution, which would actually be needed to come up with very accurate estimates of what the noise environment is. Now, with this kind of big picture idea here, think about if we are able to measure each and every noise event that occurs on and around the installation, okay, and with that information, we then can at the same time run a noise model for that situation. We then compare our forecast model to what we actually measured, and we can back calculate to learn more about the local propagation conditions. It'll take some learning time to iteratively do this process to have a good sense of the local propagation conditions and the variability of them over time. However, if that is accomplished, then I could definitely foresee us being able to use that revised forecasting model on a long-term, to do a long-term assessment.
Great. Thank you so much, Ed. Now I'd like to ask questions of both of you from a layperson perspective, and maybe Jeff, you can take a shot at this first. If blast noise is such a big problem, why do people live near the military installations?
Well, that's a great question. Well, first of all, military installations, they're a job source for thousands of people. So you can't help but have people live live around the base. I'm not aware of how many people work at some bases, but they're quite large. And there are a number of people that work there, so you can't help but have residential communities around bases.
Yeah, that's a good point, Jeff. And I think the other thing that I would add is the fact that when you, if you go back in time and see when a lot of these installations were first built, they were built in remote areas. And now over time, because there's only a finite amount of space in the U.S., we do find a lot of encroachment that's occurring. And what you actually find is that, there's some people, again, remember we talked about habituation to noise, that get used to that noise over time, but then as kind of the communities and demographics change over time, we can see how that we could bring in kind of a new type of community around some of these installations. And just to give you kind of a real-world example, there's actually been cases where, and I know that, again, the Operational Noise Group at Public Health Command has been working towards, in the Defense Noise Working Group, trying to get real estate to disclose that they're living near military installations. But you can think about kind of that sly real estate agent taking people in on the weekends when perhaps there's no noise. So you do get a small percentage of people that maybe didn't know that the installation was there. But I think more times than not, that installation, like Jeff said, has a presence. And, it's often an economic driver for that community.
Well, thank you both. Another question that we would like you to both respond to is as follows. Besides blast noise, have the systems and methodologies that you described also been applied to locations where aircraft or other military noises predominate?
So I'll start off this question and then I'll hand it over to Jeff, because I think he can give us a more thorough answer of how we might be able to. So I will simply say that no, this type of system and methodology has not been adapted into, like, let's say, an aircraft monitoring situation. But Jeff, do you want to talk a little bit about how it could be adapted?
Sure. So to Ed's point, the BAMAS system that we talked about earlier is, it's specifically designed, its initial intent as a blast noise monitoring system, but given that it is, sort of a general purpose environmental noise monitor, it can be used for measuring aircraft noise. It currently can be implemented. We actually went. During our demonstration, we were set up actually near an airport that was on base, and we put 2 noise monitors nearby and have captured a lot of data with aircraft approaching and leaving. And there's a few ways I think we could use the BAMAS system to measure aircraft. First of all, it can track them, which is fairly useful. You can a lot of times noise monitors can tell you what the sound pressure level is, but may not necessarily know where the aircraft is. So, for example, with co-located monitors around an airstrip, you can actually determine where the aircraft was during its flight path that caused high levels if that were the case. So I would say that the BAMAS noise monitoring system, given that it records raw unweighted data, it could be used to in like a traditional aircraft monitoring system to measure specific noise metrics for aircraft, in addition to providing location information.
Wonderful. And as we get ready to close, can you please give us 30-second sound bites on a parting message to our audience with an end user recommendation? So what is your take-home message, starting with Jeff, about the work that you described?
Well, first of all, I'd like to thank you, Rula, and ESTCP and SERDP for sponsoring and inviting me to talk today. I think our end users would be able to use the BAMAS system, the vital component for, as Ed said, sort of the ability to measure sound levels as it occurs on their testing and training ranges. And I think that sort of a vital component to the cycle of measure, assess, predict.
Thank you, Jeff. And Ed?
Yes, I too would like to thank you and SERDP and ESTCP for this opportunity, and then everybody who has logged into this presentation. My closing thought is more of an idea, and that is if we look at the way kind of the world is progressing, we are moving towards more and more kind of data-driven solutions. Until we had kind of this new advanced military noise monitoring system, we just didn't have the tools to measure the noise environment. We now have those tools, and it really opens up kind of the door for a realm of possibilities to, in the same way that Google can use data that's captured to predict what's going to happen or what link that you're going to click on. We can use that data to use machine and statistical learning type of algorithms to refine our predictions and come up with more accurate kind of hybrid data-driven and physics-based propagation models. It's a very exciting time, and I really, to the end users, hope that they can see how this would be a good way to move towards the management of our military news. Thank you.
Well, thank you both Jeff and Ed for a fantastic job. I'd like to thank you on behalf of SERDP and ESTCP, and I'd also like to thank our audience today. As a quick reminder, the presentation and the audio for this webinar will be archived for future reference on the SERDP and ESTCP webpage. The next webinar is on Thursday, May 7th, and it will be on factors affecting munitions mobility and in situ measurements. This webinar will feature two speakers, Professor Carl Friedrichs from the Virginia Institute of Marine Science at College of William and Mary, and also Joe Calantoni from the Naval Research Laboratory at the Stennis Space Center. At the conclusion of this webinar in a few seconds, you will get a survey reminder that will pop up on your screen when you exit. We would like to please ask you to take a moment from your very busy day to complete the very short survey. These surveys help us plan to deliver webinars better in the future. And with that, I'd like to call it a wrap. Thanks everyone again.